Join us next Tuesday, March 25, for the OPTICA Online Industry Meeting on fiber sensing. We start at 10 a.m. Eastern, 3 p.m. Central Europe. Note that's 1 hour earlier than usual in Europe because of summer time difference. We'll explore how fiber optic sensing is transforming structural health monitoring, telecom infrastructure, oil and gas, and environmental sensing. Major breakthroughs now enable real-time monitoring of bridges, buildings, and other critical structures. And as infrastructure ages, this becomes more important while keeping costs down. So the next major revolution in fiber sensing is leveraging already deployed telecom fiber for sensing applications. With fiber-to-the-home networks now widespread, we can repurpose existing single-mode fiber to create an expansive, cost-effective sensing network without additional infrastructure investments. The main issue is the amount of data generated, and here comes AI. Artificial intelligence is accelerating fiber sensing capabilities, enabling real-time data processing, anomaly detection, and predictive maintenance. By combining AI-driven analytics with distributed acoustic sensing and other sensing principles, we can reduce costs, enhance network resilience, and support smart city developments. Thanks to Tech and VPI Photonics for sponsoring this free online event. Our speakers include experts from Sintela, NEC Laboratories America, Viavi Solutions, Exhale, Lumetech, QLibri, FBGS, and Chiral Photonics. Join John Pugh and me on March 25th at 10 a.m. Eastern, 3 p.m. Central Europe to explore fiber sensing's latest innovations and its growing impact on industry and infrastructure. So let's get started. And here we are. Thank you very much, everyone, for joining the online industry meeting on fiber sensing. We are all really excited about this topic for many reasons. Some of them I just said in the video, others because this is a community. All of you are a community that have been working on this topic for many years. And I think we have a huge opportunity ahead of us. On one hand, we have seen for the first time, really telecom operators, companies like Alcatel, like Telefonica, really looking at fiber sensing technologies. On the other, companies like, I see Renko here, companies like Somni Solutions made a revolution on testing fiber sensing principles on the Genova Bridge already a few years ago. The industry is looking at us, and we have a problem and a solution to identify the amount of data that we can generate with DAS, DTS, and other sensing principles. So in the next 1 hour and a half, let's rock the world of fiber sensing. It means the world to me that we have over 100 people this morning here to talk about fiber sensing principles. Let me just say in a couple of words what we want to do here. So today is all about a meeting in fiber sensing technologies. And as I said before, Tech and the Silicon Nitride platform and VPN Photonics and their simulation software is here to let us have a meeting on fiber sensing in which we're going to do the following. This is the rules of the game. We have a few companies who are here and who have already done fiber sensing technologies. They have already TRL6 and above in fiber sensing. And to reach the next generation of iteration, they are looking for partners. And some of the partners are listed here, the enablers, and others are in the room, the 100 people in the room. What we are trying to do here over the next 90 minutes is to match the technology of Sintela, Neclas, Viavi, Lumetech, Somni, Exile, Photon First, FBGS plus Chiral, and QLibri with the technology of our corporate members. Let's see how we succeed. This meeting wouldn't have been possible without the support of all our corporate members and the hard work of my technical director on PIC and quantum technology, John Pugh, and the entire team. Today we are talking about fiber sensing. In a couple of weeks, all of those of you who are looking at imaging technologies for the food industry, stay there because we're going to have a fantastic meeting. All the rest of the topics from now until 2026 are already listed. Make sure that if you identify a topic that fits your technology, you let us know, you present, you sponsor. This platform is here for you. And also I would like to remind that all of you who became a corporate member of the last week, we have a record of like almost 30 companies for the last 15 days joining OPTICA. Thank you so much. All of those companies who are joining OPTICA, please make sure that you take advantage of all the benefits, and the most important, we have an industry library, all the presentations of all our events online and face-to-face, plus all our market reports. We have over 100 market reports are there for you. Please download them. Optica.org, all the information is there. So let's start. This meeting, as usual, is also live streaming YouTube. So let me say hello to the YouTubers of the world. Hello, YouTubers. If you have any question, write so in the chat and I will read it in the room. And that's, of course, also valid for the people here with me in the Zoom room. This meeting is as good as you want it to be. So please ask questions. If you have any question, you can do three things. One, raise your hand. Second, write so in the chat. Doesn't matter because I will ask you to voice the question yourself. And third, virtually raise the hand by pressing the button at the window that says raise hand. And with this, I think it is time to start the meeting. I would like to first, before I start, give the floor to the Technical Director of PIC and Quantum Technologies, coming all the way from Bristol, United Kingdom, Dr. John Pugh. Congratulations on putting together a fantastic agenda. What's going to happen over the next 90 minutes?
Thank you so much, Jose. Good morning, afternoon, evening, wherever you are in the world. So we're going to talk about advancements in fiber sensing technology. So exciting, accelerating rapidly, and constantly finding new applications, as you said. So to begin, I'd like to thank in advance all our speakers for joining the meeting today and being prepared to answer your questions. Please do keep them coming, as Jose says, in the chat facility. This is intended to be a very, very interactive meeting. If you could rename yourself to add your company name or affiliation before your name, like mine, this really helps with the dynamic discussions. So without further ado, we're thrilled to welcome the first speaker of the meeting, David Hill, Chief Technology Officer and co-founder of OPTICA corporate member Scintella, a company specializing in optical fiber-based sensing solutions. Recognized internationally as a leading figure in distributed acoustic sensing, or DAS, Dr. Hill has played a pivotal role in developing applications of DAS across various industries. David, please share your presentation. The floor and the attention of everyone is yours.
Great. Thank you very much indeed, John, for that introduction. Hopefully you can see all my slides. Apologies for the background here. I'm stuck in a hotel room. I'm actually attending another conference at the moment. So yeah, it's not the best surrounds, but so as John said, my name is David Hill. I'm CTO and co-founder at Scintella. And today I just want to introduce Scintella, our fiber optic distributed sensing, what that actually is and the products, and then really concentrate on many of the applications that this technology is now being used for. So without further ado, next slide, if I can move on. There we go. So Scintella was, the members of Scintella have really been looking at fiber optic sensing and DAS in particular for over 20 years. We were one of the original inventors and developers of DAS technology in some previous companies. But the whole team really has moved over. The people that were fundamental at that in those early stages are still together, and we're now all within Scintella. We're a leading supplier of distributed acoustic sensors with over 45,000 kilometers of assets currently monitored with our own products. If you look back over time with our previous companies, it's well over 100,000 kilometers of asset protected using this technology. And we work closely with partners to enable to enable our partners with this sensor technology to meet their needs in different industrial areas, and we'll come on to those industrial areas a bit later. So first, I wanted to introduce to you what actually is distributed acoustic sensing. So we take standard single mode optical fibers, and we shine a pulse of light down it, and let's run that again. And as we shine a pulse of light down it, we get Rayleigh backscatter, and we monitor that Rayleigh backscatter, and because the speed of light is constant in fiber, we can time slice that reflection back, and we can create essentially virtual sensors all the way along the fiber. And as DAS has developed, the sensitivity has improved, and therefore the length that we can monitor over. And we're now at a stage where on a single fiber, you can do well over 100 kilometers at a meter resolution. This, in effect, turns any standard single-mode fiber into an array of virtual sensors positioned every few meters. So if you can imagine putting a microphone next to your asset, whether it be a road, rail, bridge, whatever, then essentially that's what we create using DAS technology. So within Syntella, we have a range of different products. Our flagship product is called the Onyx PETA. And the name PETA kind of hints to the amount of data that this instrument produces. We can get well over a petabyte of information actually generated per day through this unit. It's what's called a quantitative DAS, which means it effectively measures both the amplitude, frequency, and phase of an acoustic signal along the fiber. And it operates on standard single mode fiber. It can operate on relatively short lengths up to 10 kilometers of multi-mode and so-called engineered fiber. And the key to this is it's also got an integrated processor built into it. So because we generate so much data, what we tend to do is process in real time within the unit itself to extract what we term as the actionable information from the large data sets. This is a 2-fiber system, so each fiber can measure up to 75 kilometers on each of these fibers independently of one another. But we can also switch the mode of this unit so it can monitor one fiber up to around about 150 kilometers or more, depending upon how it's configured. At the other end of the scale, we have a new product we've released recently, which is called Nano, which is really designed for shorter perimeters or assets up to about 10 kilometers. But similar to PETA, it's a quantitative DAS, and again, it's got an integrated processor built in. So these are the units that are purchased, and they will generate all of the acoustic data and all of the processed output all within one of those units. So that's essentially our product line. But how do we use it, and what applications are these technologies used? Well, there are multiple. One of the kind of key ones at the moment is border protection. These systems we deploy using fiber that's already deployed along borders, normally buried in the ground. We can use the sensing system to detect and, most importantly, classify activity of interest, whether it be a moving vehicle, a person walking, somebody climbing a fence, or for instance, somebody cutting a fence. And so these systems are deployed, for instance, along the US border and other borders, and have proved to be an extremely effective way of providing covert, persistent, and gapless monitoring of very large borders. In a similar vein, you can also use it for critical national infrastructure and perimeters, of course. On borders, it's typically buried, but you can fence mount it. And on perimeters, many perimeters, you would fence mount these systems. Fiber optic sensing hasn't got a great reputation in the past for perimeter security because they tended to false alarm a lot. The reason why this is very effective now is we have extremely high levels probability of detection, but most importantly, we have extremely low nuisance alarm rates, which means it becomes a very effective tool for perimeters. And again, you can detect people, fence climbing, cutting, but the important thing, I guess, is you can use the information, the geolocation of events, to slew to queue other assets such as cameras. In the rail industry, we work with partners, a company called Photonic, and they use the fiber to look at the train wheel defects as well as track defects, also such things as rockfall detection, and of course there's security applications such as railway infrastructure, people stealing the copper cable. So this gives, as I say, continuous monitoring of all of these assets. On highways, this is deployed along highways using the telecommunication that's often in place. It may be on the hard shoulder or down what's called the median strip, the middle of the road. And using this fiber, we can gather effective traffic flow statistics. So we can look at the volume of traffic, the average speed, and what it's doing to inform traffic management systems. But also we can look at condition monitoring of the road surface and have situational awareness should any incident occur, such as a crash. That we can see within the data, and we're writing algorithms to actually automatically alert on those events. In the oil and gas industry, on the exploration and production side, we're partnered with a company called Schlumberger, which is, or SLB as they've now been called, which is the world's biggest oil and gas service company. They exclusively use our product to monitor fibers that are in wells. So they use this for both passive and active seismics, flow, injection flow, and production flow, noise, cross-well strain they have in there, and many other measurands that can be detected on the fiber that is in wells. Also, we look at pipelines. So this is kind of the area where we started 20 odd years ago using telecommunication fiber that's laid next to pipelines. These quite often are transcontinental. They can be many thousands of kilometers in length, and the DAS systems monitor, and they monitor for a number of things. The third-party interference, people either accidentally or intentionally trying to get to the pipe to either steal product or do damage, leak detection along the pipe, as well as the monitoring of the location of the PICs, the pipeline inspection gauges that are used to clean the pipes. Mining is quite a new area for us, but has many applications in it. Everything from seismic monitoring to make sure that when they're doing block cave mining, for instance, that the rock is stable enough to be mined. We're looking at tailing dams and ensuring that they're not about to fail. Equipment health monitoring, such as the very large conveyor belts that are sometimes used, that's also being monitored using our systems. And we can actually track the people within the mine shaft itself. So we can detect the presence of people and machinery and give an overview to the mine operators of exactly what's going on within their mining complex. Power industry is a really exciting one. The world essentially has to double its amount of power transition within the next 25 years to meet the global demand because of EV vehicles and the drive to net zero. So to be able to monitor these pipelines to improve efficiency of transportation of power is a key thing. And that's what we do, both in being able to detect things that are happening to the pipelines, but also detecting the conductors themselves and what's happening to the conductors to improve transport efficiency. Subsea cables is another big area. You'll see it in the news at the moment. We have several of our systems employed on subsea cables, monitoring them for anchor drag and cable damage, as well as potential third-party interference. And the final application is in the science community, the geoscience community in particular. There are lots of universities around the world use the units for measuring seismic activity, earthquake monitoring, volcanic activity, as well as monitoring the cryosphere, so what's happening to the ice caps. And if you go to our website, you can see live feeds of earthquake activity, for instance, and some of the other things we did. So it was a very brief, quick run through of the various applications that this technology is currently being used for. And I think, it continues to evolve and develop as does the technology.
Thank you very much, David. Indeed, we are really living a revolution. And thank you for bringing your technology all the way from the United Kingdom. We have two people who have very good questions for you. The first one is coming all the way from Israel. We're going to the CTO of Fast Laser Technology. Thank you very much for joining us today. I would like for you to tell us who you are and what brought you to this meeting. Nahum Gilboa, are you with us? I think he's trying to unmute his microphone. Nahum Gilboa, CTO of Fast Laser Technology. 1, 2, 3, 1, 2, 3. In the meantime, the second question is coming all the way from a new startup. The startup is from Istanbul. It's called Do You Sense? Thank you very much for being with us today. Please, Serhat, tell us what's on your mind.
Hello, Jose. I wanted to know, is the sensitivity change on these devices during the length, or what? And what is the best resolution for these devices?
Well, traditionally, the sensitivity did change along length. However, with the latest systems, we're able to manage that. And over lengths of, say, 50 kilometers, the sensitivity at the front is pretty much the same as the sensitivity at the end of the fiber. So that's constantly being improved. As far as the spatial resolution is concerned, it completely depends on what your application is. Typically, on long lengths, you would typically choose a gauge length or a spatial resolution of anywhere between 5 to 10 meters. In some shorter applications where you may have a smaller perimeter, you may look for a spatial resolution of down to a meter. But it's it's all software selectable within the unit itself. So there's no fixed spatial resolution. It's all, can all be chosen by the end user.
Thank you very much. The next question is coming all the way from Mexico. This is Jorge Martinez from AT&T. Jorge, what's on your mind?
Hi, sorry, I'm on the way to the office. But my question is it possible to deploy this solution over already existing access network, for example, with real traffic?
Yes, it is actually. So most of our systems, the majority of the systems run on existing fiber optics that's in the ground, like 95% of them. Most of those systems are dark fibers, but several of our customers do use a version of our technology that operates within the L band. So they do use it on actually lit fiber. As I say, it's a minority of customers, but they're quite specialized and quite often very close to the telco operators, because no telco operator would like another system operating without them knowing how it works. But yep, the L-band systems are available from us that will operate on lit fiber.
David, Jorge, stay with us. If you like the use of a standard telecom infrastructure for fiber sensing, stay with us, because the next speaker is something that we've been really looking for. Giovanni Milione is coming from NEC Labs America. This is the research arm of NEC Corporation, and he's a senior researcher and business incubation lead for the optical networking and sensing department. We can't wait to hear not only what he does, but how we can help him doing even better than he already does. The floor and the attention of everyone goes to Giovanni, all the way from New Jersey.
Well, thanks, Jose. What a great introduction. Thank you. Just check. You can see my slides.
Gorilla Glass Clear.
Okay, thank you very much. So my name's Giovanni. I'm a senior researcher at NEC Laboratories America in New Jersey. We're very New Jersey proud, and we were just recently featured by Choose New Jersey, which is a nice promotion of tech in New Jersey, as you can see in the photos here. NEC Laboratories America is one of the several laboratories globally for NEC Corporation, which is based in Japan, which is a $30 billion year-over-year ICT corporation. And the elevator pitch we like to say is we do everything from submarine cable systems to satellites in the space and in between, like biometrics and, as I'll talk about, optical fiber sensing. I am in the laboratories in Princeton, in America, in Princeton, New Jersey. We have offices in Princeton and Silicon Valley. We have many departments doing many amazing things, such as machine learning, et cetera. I am in the optical networking and sensing department. So our kind of core expertise is optical fiber communication and free space optical communication and optical sensing. And we have worked for many years on submarine cable networks. And that is kind of where our take on optical fiber sensing came from, is the expertise in the most adverse optical environment, which is the long distance and hardship of a submarine cable. And we've kind of taken a lot of that secret sauce and put it into our optical fiber sensor, which I'll talk about today. So I am, before I was at NEC, I was actually in the United States Army, interestingly enough. So we also like to think about this from a mission critical kind of perspective for our technology. Also, just a quick shout out to OPTICA. We're very happy to participate in many OPTICA things. I used to be on the editorial advisory committee for Optical Photonics News, and I'm currently a topic chair for Frontiers in Optics. And if you want, please submit to Frontiers in Optics, the deadline coming up in a couple months. We're just shout out, we're very happy to participate in all optical events. So thanks, John and everyone for inviting us. So our kind of, the way we frame the problem for optical fiber sensing as a corporate laboratory is what we're trying to do is sense everywhere, everything, all the time. And that veritably is like creating a digital twin. And this kind of creates the ability to do real-time and ubiquitous situation awareness for many use cases. To accomplish that, of course, at the core is you need sensors. Canonical sensors are prohibitive, or they're great, but they also have limitations. Like electrical power, communication, synchronization, and they're adversely affected by the environment. So if you wanted to sense everywhere all the time with electronic sensors, it would be tough because you'd have to scale them in a way that's prohibitive. So today, with our expertise in optical fiber communication, we understand that optical fibers are now ubiquitous, from submarine cables to terrestrial on land, to within cities, to even within buildings like data centers. And after many, many years of research by the entire industry, we now know everything about optical fibers, and we can control all their properties. They're low loss, and they're everywhere. So our take is, can we use existing optical fiber infrastructure, but not obviating new optical fiber infrastructure for sensing? And this is kind of a schematic of how we do it. And thanks, David, for the great fundamental introduction, how it works. We are leveraging many of the effects in an optical fiber, such as Rayleigh, Brillion, or Raman scattering. But we have, as David described, a interrogator, which is a single optoelectronic that's a device that's centrally located. I like to say it's similar in size and use as an Xbox or PlayStation, because it's about that size, and you plug it into the wall the same way. And you plug one end of a fiber into it, and it veritably converts the fiber into thousands upon thousands of acoustic sensors that are no different than accelerometers, geophones, or microphones. And in fact, all of those at the same time. And it can do that over scales of even 100 kilometers. It creates this massive acoustic data. Then we apply some artificial intelligence to it. In a way, the same artificial intelligence that NEC applies to biometrics, satellites, and everything else. And then we spit it out onto a consumable and easy to use dashboard. And so there are many use cases of this, which I'll go through. The exciting thing, I think, in the past 10 years has been the use of AI to kind of, I like how David put it, we get from what was considered a problem with optical fiber sensors to now it's becoming equal to or more effective than regular sensors, because we're able to solve things like probability detection and nuisance alarm rates. And just kind of a sign of that, there's this great series on TV right now, I don't know if anyone's watching it, called The Agency, and they had a whole scene where one of the main characters is talking about distributed acoustic sensing. So distributed acoustic sensing is now coming to the mainstream, which is kind of fun. So I'll go through a couple use cases that NEC has been focusing on. And again, our core has been optical communication. And so we are trying to leverage the existing telecommunication infrastructure of optical fibers to do some sensing. So some of the first things that we did some years ago, we have a public and large partnership with Verizon, and we are plugging in our interrogators to the networks of Verizon. And we're able to, when we do that, I'll show you some optical fiber sensing data. We're able to sense everything around the network, such as traffic, et cetera. And then we also are now, what's kind of fun is we're kind of extending that into what they call IOWN, an all photonics network, which is a consortium of telecommunication companies globally that are envisioning the next phase of telecommunication networks, and optical fiber sensing is now becoming a core part of that. So we are really excited to see how this is going to scale, not limited to, but definitely motivated by the use of the ubiquitous and existing telecommunication infrastructure. And so this was one of the first works that we did regarding this. We plugged in our distributed acoustic sensing interrogator to approximately 100 kilometers of optical fiber in a Verizon network. And when we plug it in, all that fiber is kind of already deployed along rights of ways of roads, et cetera. So we automatically see things like vehicle traffic, What we did, which was really good, is we tried to see if we could monitor traffic, counting cars, traffic flow, etc., with the same efficacy as a video camera on an easy path toll booth. And the slide and the figure on the bottom kind of shows that when we apply our AI to our distributed acoustic sensing data and compare it to what a video camera on an easy path toll booth does, they're basically 1-to-1 is what that graph's showing. And that's really exciting that we're getting the efficacy of these other sensors with optical fiber sensing, of course, continuously and ubiquitously along the infrastructure. And then in addition, we can do things like determine the quality of the road and potholes, which we apply some simple, in this case, artificial intelligence, like a support vector machine, to determine the size of potholes along the road. And we did all this while transmitting a super sexy communication format, like probabilistically constellation-shaped super high QAM or something. So this is kind of one of the first works that we did. More recently, we started plugging into other networks, such as an optical fiber network in New York City, which is a lot busier, but we still see similar things, such as subways, vehicles, etc. We even see some abnormal signals in it. And this is just showing what else we can do. And the interesting thing about this is this network is kind of a test, is like a field test in a way for the future of these ion or all photonic networks with these very high speed commercial 400 gigabit per second transmission technologies. So again, we're trying to show that the optical fiber sensing, distributed acoustic sensing can live with the existing telecommunication infrastructure. And then what we also kind of did over the years is we plugging into many different telecommunication providers' networks. We can detect things not just like traffic, but also is there what the telecommunication provider is interested in? Is someone going to dig up the fiber cable or damage the fiber cable? We don't want to know if they did it and where they did it, but we also want to be able to preemptively prevent it. So in this diagram, you can see the zigzag lines of the traffic signals detected with our distributed acoustic sensing along many kilometers of a road. And then you see there circled in yellow, the strikes from a construction vehicle that's digging right near an optical fiber cable. And then applying our artificial intelligence, we can try to locate it and see it before it actually hits the cable. And the plot in the bottom is doing that over a long length of time, providing the telecom operator a lot of statistics about what's going on along their cable. Then, of course, we could do lots of other things aside from just monitoring traffic and looking for, is someone going to dig up the cable? We could also determine where manholes are and some other ancillary things like that along the network. So this is, again, many kilometers of optical fiber from a telecommunication infrastructure along a highway, and we are applying our artificial intelligence to the distributed acoustic sensing data to determine the location of manholes. And the location of those kind of network elements is very important for a telecom provider to understand. And then finally, one of the other use cases we did is traffic monitoring explicitly. So NEC has a large relationship, of course, with many entities in Japan. So now we have a public and large partnership with NEXCO, which is like the Federal Department of Transportation in Japan. And our optical fiber sensors, our distributed acoustic sensing, and also our distributed temperature sensing is being deployed over all the highways in Japan through NEXCO. And you could see the distributed acoustic sensing data on the bottom there. This is the NEXCO, their Department of Transportation's fiber optic for their traffic network that's used to get data from traffic lights, other sensors. And we plug in our interrogators to that existing telecom network, just like we did with Verizon, and we can see traffic all over the roads. And they integrate this into their command and control stations. And it gives them, in addition to the sensors that are sparsely placed along the road, this continuous monitoring between, which has been very disruptive for them. And then, of course, we can do some other ancillary things like determine the quality of the roads in terms of weather, and also if vehicles are running off, et cetera. And again, it's a combination of our distributed acoustic sensing expertise that came from submarine cable networks and our artificial intelligence expertise together. That's kind of the secret sauce, creating all these use cases and this kind of scaled deployment, both for telecom, for traffic, and for many other things. So what can we do for others and what can others do for us? So I think the key word is collaboration. Being in a large corporation, we fully understand we can't do everything ourselves. We're not supposed to do everything ourselves. So we have in the past collaborated with universities government entities, and other companies. So we are very open to collaboration like that in the future. So feel free to reach out if anyone has any interest. So thank you very much. And thanks again, Jose, John, and Helena for the invitation. Optic industry is amazing. Optic in general programs are amazing. I've been participating for almost 20 years now. We're going to keep doing it. So thank you, everybody.
Thank you so much, Giovanni. We have a question in the chat from Jake at Light Trace Photonics in Bristol in the UK. Jake, do you want to unmute yourself and ask?
Yeah. Hi, thanks. Yeah, that was really interesting talk. My question is, it seems like there are some really cool applications of DAS. I'm keen to understand what new applications might be enabled or perhaps enhanced if photonic integrated circuits were to enable more stable or cheaper deployment of these systems.
That's a good question. So what actually Japan puts into the interrogators, I don't know, because after we invent it, they do whatever they do to be able to scale it and all that stuff. Clearly, photonic integrated circuits have been an enabler for other kind of technologies, such as optical interconnects in data centers, because of their ability to lower the cost, because they're scalable, because they're able to be manufactured on the very scalable CMOS platforms. So I think, of course, that is going to be something to think about towards the future. And I think there's, over the past couple of years, there's been a few publications about fiber sensing and photonic integrated circuits. So I think it could for sure have some advantages.
Right. Cool. Thank you, Giovanni. So we had a question in the chat about the chemicals you mentioned. Alina, do you want to ask the question?
Hello, do you hear me?
Yes.
Sorry for the delay and sorry for missing the beginning. The speaker told to us that they used the chemicals in the optical fibers. How did they use it and how potentially might harm the environment, or what's about? I did not understand correctly. I mean, fully this aspect. If this question if the question is too difficult and the answer is too long, please give me a link and I can read by myself.
Thanks, Alina, for your question. So I think in general, one of the core value proposition of optical fiber sensing, the way we're doing it, is that we have the same value proposition as optical fiber communication, which means that we have these low-cost cables that do not adversely affect the environment, that are scalable. So of course, glass is doped with something to make the optical fibers waveguiding, but those things are kind of embodied encased in cables, etc. So they don't really have that kind of adverse effect to the environment, if I'm understanding what you're asking. But thanks for your question.
Great, thank you so much, Giovanni. So we're gonna move on. We'll come back to some of the questions later. So it gives me great pleasure to introduce Andres Chavaria as the Market Development Manager, Fiber Optic Sensing North America at OPTICA corporate member VRV Solutions, bringing over 2 decades of experience in engineering fiber optic sensing solutions, geophysical, earth science, and infrastructure monitoring applications. Dr. Chavaria focuses on market development for fiber optic sensing technologies, aiming to enhance testing and monitoring capabilities across various industries. Andres, please share your presentation. The floor and the attention of everyone is yours.
Thank you, John. And also thank you to Dave and to Giovanni for giving that excellent introduction. That will give me some valuable time. And really, I think following on Giovanni's message of, well, how can we take advantage of existing telecommunications infrastructure to do more sensing? And I just wanted to put this in context a little bit of where the deployments of fiber sensing have taken place over the last, I want to say, 20, 25 years. And I want to say probably the largest adopters were certainly pipelines, which was oil and gas, as they mentioned, and of course, utilities, power cables, large volume. There's been a lot of deployments on this area. The other users of the technology have included things like borders, perimeters, a lot of stuff for the oil and gas industry, which I would say they really pushed the technology many levels. And that has also taken us to the subsea market. And the one where we have the least adoption is telecommunications. And this is interesting because I think this is the one that has quite a bit of fiber. So if we were to put if we were to think about the amount of fiber that is available, we would say that maybe between pipelines and power cables, which are mostly fibers dedicated for monitoring, we're probably looking into the hundreds of thousands. I would say way less than 1 million. They've shared a couple of numbers on that. The other applications, perimeters and borders, we're probably looking at 150, 300,000 kilometers. Borders, just so you know, our land borders, it's around 140,000. So I'm actually being quite generous saying here that there's a lot of other fiber potentially up for grabs for sensing. Subsea cables, we're only touching them right now as far as monitoring, but we have around almost 1.5 million kilometers of subsea fibers. But really here, the big fiber deployment, which is really what we need for fiber sensing, it comes from telecom. And in telecom, we are really looking into millions of kilometers. So this is really uncharted territory, fibers that we barely have touched. And I think there's a lot of opportunities. So here I wanted to talk about what is happening there, why this may be. Giovanni talked a little bit about this. And just from our point of view, certainly within Viavi, we are basically already touching a lot of fiber. So we have almost 2 million instruments testing fiber worldwide. We have almost 8 million kilometers of fiber that is being tested or monitored with our traditional telecommunication devices. And again, this is a very large opportunity to basically say, well, how do we scale this? How do we add sensing into this? Dave and Giovanni already showed some of the applications of the technology. And here, what I want to address is, well, what is needed really for a scaling and further adoption of these tools? So as I mentioned right now, as part of our optical network monitoring systems, there are different components. Again, historically within a telecommunications environment, we're doing a lot of assurance, a lot of compliance of our network building. So again, checking all of our connections, checking all of our ports, checking all of our switches, more on the construction side. We're basically also doing all of the fiber monitoring. A lot of our monitoring really has focused in telecommunications on things like fiber breaks or things that are more catastrophic, where essentially you lose a line and then you need to try to reroute it. And that's basically the extent of the monitoring that takes place to ensure that we can transmit data from one point to another. And of course, tied to this, we're going to have all of the analytics that goes from trendings, looking at, well, how else can we monetize a network when they are in a specific urban environments or whatever. And the next step, I think, on this network monitoring is sensing. Again, we are taking advantage of these fibers that are already in our conduits or in our poles in aerial grounds. And basically, the distributed sensing basically adds a lot of potential to monitor these assets. So of course, we have fiber strength, which we can use for things like detecting cable conditionings, loading in forests. I'm in California, so trees are a problem in some aerial lines. Icing for those of you who are in the northern latitudes. Temperature, the same. Again, another example from Los Angeles, locating fires, again, in those aerial lines that can put the fibers at risk. So again, we can start to really think about testing all of those fiber optic cables beyond a traditional OTDR, which is basically what we're doing with sensing. Again, we're monitoring the environment surrounding those fibers. Dave and Giovanni already talked a lot about acoustics. And again, right now, probably the main use case, the easier one, the one that is easy to grasp is, of course, intrusion detection, detecting the excavator, detecting the person who's going to try to come and steal your cable. Those are the things that we can basically use with acoustics. But again, these are technologies that we can actually connect to our fiber optic sensors, and basically they will allow us to do things that are beyond the capability of traditional testing equipment. So just as an example, here I have an area line where we're basically running an OTDR. So the OTDR looks just a regular losses, nothing particularly exciting. But when you look at something like the strain data, in this case, we're using a DTSS, distributed temperature and strain sensor, we basically start to see that along that fiber, this is almost 90 kilometers of fiber, we start to see a lot of these steps because essentially the line is being loaded by ice. So you can imagine that as this line starts to get loaded and then unloaded, the fiber, the cable, starts to get weakened. So the intention of this type of surveillance is more of a real-time surveillance, is to ensure that the cable is not degrading too fast, or we can actually service these lines before they fail. I think the value proposition of sensing is preventing a failure, ideally, by this monitoring. Won't go into much of the details. Giovanni already mentioned this, but of course, we have, as part of our distributed acoustic sensing, we can detect the excavators, ideally, before they go and cut a cable, so we can actually raise an alarm and basically tell the operator, just contact this crew before they start to do everyone. For those of you in the US, we have the 811 system. So it's a very complementary aspect to that, to ensure that not only our underground, but also our aerial lines are operated safely. So how else, again, what can get that? Could you try again? So what can happen for these things to when it needs to take place to take advantage of this telecom infrastructure? So something that we have done within Viavi is basically build our testing, our modular or sensing systems in a modular fashion. So what this means is that if we have a network operations center, we can actually are already going to have devices where we can actually just include the module, the interrogator, basically here as the scale of my hand, that we can just plug into this telecommunications hardware and start to do sensing, just as if it was another operation that we do in these control rooms. If you don't have, let's say, a network control room, maybe you you need to go and test a fiber, maybe with a handheld technology, where essentially you can put that same module, instead of putting it in a rack, you can put it into a handheld unit. So you can send basically engineers and test and monitor fibers for specific uses. So this really allows us to be very versatile as far as the types of fibers, the types of environments where we can monitor these things. We are already operating within data centers, within network operation centers. And again, this combination of modules, whether it is a DAS, whether it is acoustic, whether it is a strain, whether it is temperature, really allows you to really monitor those fibers depending on the environment of where they live and the type of applications that are needed for that. And at the end, we're really aiming to have a very integrated fiber testing system that really goes beyond that testing, but really is more a full-time surveillance of those fiber optic networks. Of course, that's the hardware. There's always a software. Again, we operate very, very large networks worldwide. And they basically share this principle when we are looking at our network monitoring systems, where we have our interrogators pushing data, pushing some alarms into the cloud or into different local networks, where essentially in this data analysis, what is going to happen is that we are going to not only have the diagnostics for the fibers, but we can actually start to do a lot of fiber analytics on, well, how are our optical networks behaving with respect to time? Which segments may be at risk? Which segments need some level of maintenance? And something that is very key within telecommunications is that, and it's usually a challenge when you're dealing with these types of cables, is that we need very, very good GIS capabilities. So within our environment, since we're already monitoring these very, very long networks, we can already start to basically georeference all of our alarms. So basically the operator of that network basically can use sensing to have that alarm system. In this case, for an excavator, here was a cable where the operator thought the excavator was in a different location. And this basically allows us to do some preemptive surveillance before the fault comes in. It's another example where essentially as part of our notification system, again, these tools are basically being used to monitor thousands of fibers. Imagine a data center that has thousands of ports. We're using all of this existing infrastructure that came from our telecommunications work, but now all of a sudden we can start to use, I'm going to add temperature, I'm going to add a strain as part of my diagnostics. So we can basically detect anomalies along a fiber. And again, depending on whether we're looking temperature, strain, we're basically going to be detecting, in this case, it's a strain anomaly, probably maybe from a tree that was touching an aerial line or something like that, or an excavator, you name it. So this is already part of the ecosystem that allows us to do fiber sensing. So in the end, what we are basically now, the change in perspective here is really taking advantage of a very mature fiber testing ecosystem and really adding sensing as a service and as a very critical service that will allow us and increase the longevity of these networks. So really, I think for all of you in the audience, I think the paradigm here that we want to address is really take fiber sensing beyond fault detection. We can detect from an OTDR if a cable is cut, but we want to basically prevent that fault from happening. So I think what fiber sensing provides is that philosophy of fault prevention instead of fault detection. So thanks, John. Thanks, Jose, for the invitation. And there's my email and my contact info.
Thank you very much, Andres, for being with us. The first question coming to you comes all the way from Germany, from Karlsruhe. Jörg from Nanoscribe, what's on your mind?
Hello, everybody. Nice to be in this meeting. I have a general question is how fast is the time between detection of a fault, so basically excavating or something like this, informing someone, and how do they know it's somebody who's excavating and it's just not a truck passing by? So how is this happening exactly? Because all three companies have now shown nice diagrams of some signals, but I'm wondering how then somebody being at a screen getting a signal knows what does it really mean?
Yeah, no. So that's an excellent question. And really, depending on the instrument, the response time will be different. Temperature and strain are usually longer processes, but DAS specifically, DAS is the most dynamic. DAS basically will allow you to detect an anomaly within a couple of seconds. And depending on the detectors that we basically implement to this, you're really looking into seconds. You start recording the signal, you have a few seconds, raise an alarm, and then if the system is properly integrated, you will have a notification in an email or a text or in a control center pretty much automatically. So there are certain signals that may take a few more seconds, maybe a couple of minutes to build, but for the most part, they are very, very dynamic, which again, that's what makes it so useful for preventing an excavator. The next question will be, well, how do we notify the operator of the excavator to basically stop? That's a different story, but as far as reaching out to the control room, these notifications are basically running, I'm going to say, in near real time. Again, within a few seconds that you can actually take an action on it.
Andres, the second question comes all the way from France, from the specialty fiber region of Lannion. Mathieu Bergond from Exile, what's on your mind?
Yeah, I was wondering, how does the response of your sensing instrument vary if you change, for example, the structure of the cable that holds the fiber? I think someone asked about tight versus loose structure.
That's a very important question. For the most part, DAS will play with any type of fiber. I could say that things like a tight buffer fiber are more suitable maybe for strain measurements. So we are looking into ground deformation, into that type of application. Tight buffer may be a little bit more useful, but we don't have as much tight buffer, certainly within telecommunications work. So I think there's different techniques really to assess the signals from either type, but for very specialized uses, if you want really focused temperature, you want really focused strain, the choice of fiber may be more important. DAS, for the most part, is very versatile and can connect to it. You will need to interpret the data, so that's a challenge that will come up. Well, how much of this is temperature versus strain? So that's something that the choice of fiber will play a role on.
Andres, stay with us because in a couple of presentations, Matteo is going to talk about the kind of things they can do at Exile, in gravitometry, in energy management. You will be amazed. But before that, allow me to continue on the topic of AI. And for that, our next speaker, Zach Spica, comes from Lumetech. He's the CEO, and he is harnessing the AI-driven insights to deliver situational awareness. Thank you very much, Zach, for being with us. The floor and the attention of everyone is yours.
Thank you, Jose. So let me share a stack. That should be all right.
Yes, yes.
All right. Well, thank you, everyone, and great presentation so far. That's a really interesting session that we have today. Thank you for also giving me the opportunity to be there and to showcase what we do at Lumetech. So we are a pretty young company. We actually came out of stealth in late January. So we are like a few months old in terms of products. But we have been building that over, we are kind of a spin out coming out of University of Michigan, Caltech, and Google, where we have led a lot of research on subsea fiber optic sensing. Some of our members have been actually writing some of the most influential papers in long-range sensing in order like to transform the full length of the fiber into like arrays of sensors. And other members of our team are actually been working in the government and at Google, laying down fiber, subsea fiber, and so building like business development cases for the telecom industry. So we are very focused on telecom and subsea fiber in general. And we are now headquartered in the Bay Area, in the Silicon Valley. And we have decided to convert those years of research and ideas into a purely software engineering problem. And so we came down to narrow down our mission to something very specific and narrow, which is we want to protect subsea infrastructure at all costs. And we will that through fiber optic sensing, but we will that through many different data input as well, because we realize that if we want to protect this infrastructure, sensing as a service is great, but it will not solve the telecom problem. And so, yeah, how are we going to do that is really through developing enhanced software for situational awareness and telling our customer what's happening along the fiber. And so let's talk about like the real problem. No, they are as Andres showed just before, there are about 1 million mile of fiber at the bottom of the ocean. This is a 100 billion infrastructure that the telecom industry has been building for the last 30 years. And there are about 600 fibers in total just for the telecom. And those fibers, they break all the time. They are fragile and it's easy to break, accidentally break. And most of these outages or fiber fault, they cost like millions, in average 1 to 3 million to the telecom industry to repair. So if we can save one of these outages, then we bring a lot of value to the telecom customer. The good thing is that most of these outages, they are actually caused by human interaction. They are accidental. We have heard recently that they are sabotage. We are joking that Vladimir Putin and Xi Jinping are our best salesperson right now because they make a lot of noise around these fiber outages. But let's be clear that most of it is accidental and mostly due to human interaction on top of these fibers, like fishing nets dragging on top of the fiber or boats dragging the anchor. So that's really our target. That's what we want to stop, and that's what we want to prevent. But as I said, like fiber sensing as a service alone will not solve this problem, because yes, you can have like some information, you can know what's happening along your fiber, you can know there is like a vessel that is approaching, you can track them in time and space, but who are there when they have like the GPS or the beacon off? How do you recognize them, and how can you actually transfer the liability from the telecom industry, the telecom owner, to actually the culprit that may provoke an accident? And so for that, that's why we are now merging many different data sources that are available, including satellite data, including radar, or including as well long-range sensing to learn what's happening past the first repeater, where DAS and distributed acoustic sensing is not useful or available. And so here is an example of our software where really we detect boats, and thanks to satellite images, we can actually track them, have their flag, have their identity. And so we will build up like a catalog of who are the rogue actors, who are really the actors that are having a behavior that is dangerous for the telecom industry owner, the telecom asset owner. So our product, which is really tailored for the telecom subsea industry, we offer like 3 pillars, which are like threat detection, so real-time monitoring of surface and ground movement contact activities that could harm the fiber. And what's really important here is that we have surface and ground contact, and that's where fiber optic sensing will be important, because if there is a boat crossing on top of the fiber, that's not an issue. But if there is contact with the ground that we can detect with long-range sensing or DAS, then that's going to be really triggering an alert. But then who are there? That's going to be learned through other type of data inputs. And that's really like the highest bar to clear is like, how do you stop an outage? Like sometimes we only have a few minutes, a few hours. So it's possible in some very specific cases, if you're near the shore, if you have like the help of the Coast Guard, but in most of the cases, it's going to be very hard to stop this damage to happen. So we are also working on long-term deterrence. And long-term deterrence really is about like having automatic intervention protocol first, but also providing intelligence to the owner, knowing exactly what's happening in real time, but also through long period of time, narrowing down who are the culprits, who are touching your fiber repeatedly and having like near misses over like the years, no? And so then we can work specifically on a few very targeted individual in order like to build awareness and make this behavior change. Third component is as well like health monitoring of the fiber. Many times fiber owner, they don't really know where they should actually apply the maintenance, where they should apply repair. With fiber optic sensing and other technologies, we can actually know if there is a strong abrasion. We can know if there is like some traction, if the fiber is buried or unburied, etc. So we provide more information on that. And really to insist here, so what are we detecting with our technology, which is important for the owner, for the telecom owner? It's like seabed contact, dark vessel, and so vessel with no AIS or beacon, dark vessel, but also the identification, who they are, even if they are dark, and building up these profiles of bad actors in order to transfer the liability. We can detect anchor drag and bottom fishing, but also if there is like sabotage of activity near the fiber. So I wish I had time to show you a demo of our software. So we use fiber optic sensing as a core component, but we have decided to make total abstraction of fiber optic sensing in our software. We think our customer doesn't need that type of information. That's too much information. The only thing that they need to know is who are the bad actors, what's happening in real time, and different layers of alerts with identification of the rogue actors. If you are interested in a real-time demo of our software, I would be happy to do so. You can contact us directly via email or find more information on our website.
Set speak at lumetech.com, you will receive a lot of requests for this demo, but allow me to highlight one. We have in the room one of the most well-distinguished consultants in contamination control, Mark Kamenzind. What's on your mind? Mark Kamenzind from Kamenzind Solutions. He's trying to unmute the microphone. So allow me to come back to him. And while we do that, we have a lot of questions related to comparing DAS, DTS, and other sensing systems. The best way to do that is to listen to the next presentation. Allow me to go all the way to the Netherlands and meet Renko Nieuweland, the CEO and founder of Somni Solutions, and one person who really have a beautiful success story on the monitoring of the Genova Bridge. Renko, thank you well for your time. Thank you for being here with us, the floor, and the attention of everyone. You're a really good friend of mine. Thank you for being here. The attention is yours.
Hi, Jose. Thanks for the kind introduction. Thank you for allowing me to show a few slides of actually quite an old project which we did together with partners on monitoring the Genova Bridge. This was actually one of our first mainstream projects which we did as a company, because we were founded in 2017, and this bridge collapse is from 2018. Just to recap a little bit, in Genova there was a bridge which collapsed in 2018. This was the Morandi Bridge. It's quite a disaster because there are, as you can see in the photo, there are some houses underneath the bridge. So there were quite a lot of people killed due to this bridge collapse. In addition, this bridge is a major artery for Italy, and has therefore tremendous amount of economic value. So a new bridge had to come quite soon. The whole bridge was demolished in June 2018, and there were plans to make the new bridge the San Giorgio Bridge. And the first deck, that bridge went really fast, was launched on October 2019, as you can see here. And it was finished on the 28th of April 2020. So yeah, that's quite impressive for such a huge civil engineering structure. These are some tests which you can see on the photo with a massive amount of trucks loading the bridge. And it was opened for traffic on the 4th of August 2020. Nice photo here of that bridge with the Italian flag. So, of course, this is a smart bridge, so it's filled with fiber optic sensors, not just from us, but also from companies like Luna, which also provided interrogators, accelerometers, and from the Slovakian company Silex, which provided a large number of strain sensors, which are all mounted across this deck. This is a cross section of the deck, as you can see. For Somni, we provided a large number of tilt sensors, and to be honest, though, so I just mentioned we were a startup company back in 2018, and I must admit I bullshitted a bit that we had very good tilt sensors, which we not yet had. So we were developing, and this was actually our first launching customer. Providing 76 tilt sensors to be installed across that bridge. You can see a photo of all the tilt sensors we provided. They were mounted into these enclosures together with accelerometers from Luna, and installed on the top and on the bottom of each pillar of that bridge for continuous monitoring, 365 days per year, 24/7. And that monitoring is ongoing as we speak today. It's now 5 or 6 years that stuff has been installed, and the monitoring is still continuing without dropping a single data line. So it's working very nicely. This is an overview picture of the whole bridge. It's quite long. There are quite long fiber optic cables running across the bridge. There's some redundancy built in, and in total, you see the number of tilt sensors, 55 accelerometers, 44 strain sensors, continuously monitoring and safeguarding this bridge to prevent what happened in 2018. I think this is a very nice example of fiber optic sensor companies working together, providing different types of sensors, interrogators, to jointly come up with a full solution for a bridge. So yeah, thanks again for Luna, Silex to work together on this specific bridge. And I hope for the upcoming years we can continue monitoring this bridge proactively and avoid any issues in the future. That basically drops down to the end of my presentation. I want to thank you for your attention, and if there are any questions, please let me know.
Remco, thank you so much for your presentation. It's actually a bridge I've personally been over, and it's a great example of collaboration between companies. There's been a number of questions actually in the chat relating to distributed temperature sensing, distributed acoustic sensing, fiber Bragg grating sensing. How would you sort of compare them all briefly?
I think then you have to look at the application. So we are using fiber Bragg ratings for all our sensors. We are always converting a physical parameter of interest, such as tilt, acceleration, temperature, displacements, to strain on the fiber, specifically the location of the fiber Bragg rating. So we are a company which makes those type of transducers to really measure a specific parameter at a specific point. If you look at distributed sensing, then we're talking about large distances, kilometers, like the previous speakers have shown, and very specific parameters, temperature, strain, acoustics, and it's spread over a little bit more distance than the specific point sensors which we are using. So here we're talking about a few meters, and with for a distributed acoustic sensor, for example, and if you compare that to a fiber Bragg rating based accelerometer, that's really a point sensor. I hope that answers the question.
That's great. We have another question from Bram van Ho at FBGS. Bram, do you want to unmute and ask?
Sure. Thank you. First of all, Remco, for the great presentation. I was just wondering, you of course present a number of gratings, number of sensors that are being interrogated by, in this case, a Luna device. Were you hitting the limits with respect to the maximum number of measurement points you can read out? Or in other words, is there a need to further expand the interrogation capacity with respect to the number of gratings and sensors when targeting this kind of project in the future? Can you share any comments on that?
So indeed, there's a Luna Hyperion system used here for this specific bridge, and it's pretty much filled up with how much sensors you can hook up to that specific system. If this bridge would need more sensors, I'm not sure. I'm not a civil engineer,
right?
But I think having the capability of adding more sensors, more fiber Bragg ratings to a system like that could be very beneficial. Yes.
Okay. Just to add one comment, we're building their platform, our Infinity Scan, that is exactly doing this, further increasing the number of gratings, bridging a bit the gap between distributed systems and FPG-based systems. It's not a topic of my talk today, but we can of course cover this in more detail if you see an interest in this kind of project to expand or increase the number of FPG measurement points on a single FPG line or optical line.
Great. Well, thank you so much, both. We can take that offline later. So next up, we have Mathieu Begont, Specialty Fiber Product Line Manager at Exail. OPTICA corporate member Exail is an expert in the design and manufacture of state-of-the-art optical components. A solution exists for many sensing applications based on photonics, gravimetry, energy management, inertial sensing, distributed fiber sensing, environment mapping, and scanning. And also harsh environments. Welcome, Mathieu. Please share your slides. Tell us more.
Thank you, Adrian, for the introduction. Thank you for giving me the opportunity to present what Exail is, what we do in the field of fiber sensing. So just a few words about what we do. So we are a French-based company, a bit more than 2,000 employees now. And as you guys can see, in terms of markets, it's very diverse. So today we will, of course, very much focused on the photonics activities. So we do optical components, so COTS components, and we have three big families of products. So lithium niobate modulators for amplitude or phase modulations. We also have micro-optics assemblies, for example, for coherent detection, polarization control, and so on. And we do specialty optical fibers with here again three subcategories, so active fibers for lasers, for example, PM fibers, and passive fibers. So we do these optical components in-house, and we also do instruments that heavily rely on these components. So Excel has a long history of making fiber optic gyroscopes. So those are inertial navigation system. Basically, they tell you where you are at any given time without GNSS. And if you're not familiar with fiber optic gyroscopes, it's essentially 3 rotation sensors and 3 accelerometers. And with these 6 sensors, you can know where you are in real time without GNSS. And for these fog instruments, the rotation measurement is done using fiber optics. So you can see here on the right side, you have like a schematic of a fog instrument, and you can see the coil of optical fibers. So that's typically a couple of 100 meters of fiber that is being used to measure rotation. Why specialty fibers for sensing? Really, it's a complement to standard telecom fibers. It's not meant to replace, of course. When you can use standard telecom fibers, it's still the preferred option because it's very cost competitive. So specialty fibers come into play when you require a specific waveguide or a specific geometry, or you want a coating material that is not the standard acrylate coating that you find on standard fibers. So you can see here on the top right, it's an illustration of cross-section of different types of fibers that we manufacture. So you have different cladding size, the standard being 125 micron, but you can have much thinner fiber, so down to 40 micron, or much larger fiber up to a couple of hundreds of microns. And with within this cladding diameter, you can have different waveguides. So of course, you can have single mode fiber, you can have multi-mode fiber, and you have a lot of degrees of freedom by taking the waveguide that you want, the cladding size that you want, and the coating material that you want to really tailor the fiber to your application. So the coating material, there are different aspects, but really the main thing is the maximum operating temperature. So as you can see here in the picture at the bottom, so polyimide can go up to plus 300 degrees C versus high temperature acrylate that is limited to plus 150. And then if you want to go above plus 300 degrees C, you need to switch to metal coatings such as aluminum that can withstand plus 400 degrees C. So just to give some orders of magnitude, here in Lannion in France, we manufacture a bit more than 10,000 kilometers of specialty fiber per year. As you can imagine, there are lots of different references. So 250 references from stock, and we do both high volume production for our internal needs for gyroscopes, for our customers, and of course, we do a lot of draws for custom designs. So now focusing a bit on harsh environments. So what do we mean by this? So it's either extreme temperature, so it can be cryo, it can be very high temperature, it can be the presence of radiation, chemicals, or gas. And as you've probably seen, there are conventional environments, and then we put fiber also in harsh environments. It's already the trend, so it's not in the future. So for temperature, it's mostly the coating material that is the limiting factor usually. And for radiation, there is an illustration here in the middle. The fiber tends to darken. So this is called radiation-induced attenuation. So basically the attenuation increases because of radiation. And to mitigate this effect, we have what we call radar fibers. So we have, you have on the top right here an illustration of different radiative environments, depending on the dose rate in the horizontal scale and the dose. And you can see it's a very wide range of doses and dose rates. So you have space with extremely low dose rates and extremely low doses. And at the opposite spectrum, you have fusion experiments, for example. It's a very hot topic right now. like inertial confinement fusion, where you have extremely high dose rates. And this is also what we see on the images on the bottom right. So the laser megajoule in France and NIF in the States, where they're using our fibers to monitor those experiments. And you have more than 10 to the 18 neutrons in less than 25 nanoseconds. So as you can imagine, the fibers need to withstand these environments. So for harsh environments, we rely quite heavily on a joint laboratory that is based in France, where we can really focus on the fundamental level. And really the objective is to gain this fundamental and physical understanding to improve our products and to have access to a lot of irradiations for process control, so what we manufacture today, but also R&D activities for what we'll manufacture tomorrow. And this is my last slide. So I'm trying to answer the famous OPTICA question. So what we can offer COTS, photonic building blocks for both interrogators and fiber-based sensors, so with specialty fiber. We have solution for standard environments, but also harsh environments, both radiation and temperature. And also with fiber, there is always this barrier of custom developments. So there is what is available on the website, but we have also many references in stock that are not shown on the website. So if you have some requirements, don't hesitate to contact us, and there is probably something close to what you need available. And as an industry, I think what we need to do is strengthen the collaboration between cable manufacturer, so specialty fiber manufacturer, and interrogators. Because the spec of the complete system depend on all aspects, so fiber, cable, and interrogator, of course. And for harsh environments, the fiber can withstand temperature up to plus 400 degrees C, for example, but there is really a need to package this fiber in most cases, and those packages need also to withstand extreme temperature and radiation level. So I think there's still some work that can be done on this side. And that's the end of my presentation. Thank you very much.
Great. Thank you so much, Mathieu, and the incredible work that you're doing at Excel, and particularly for preempting my questions. So we're going to move on to welcome Photon First CEO Leendert Jan Nystad to present their next generation fiber optic sensing solutions based on PICs, or photonic integrated circuits, which enhance reliability and enable compact, scalable solutions, easy deployment in some very harsh environments. Leendert Jan, welcome. The floor is yours.
Thanks, John, for introducing me. I'm happy to report to Giovanni, one of the previous speakers. PIC-based interrogators are not just research environment tools and publications. They're actually there, and it's called Photon First. So I'm going to tell you a bit about where we stand today. Photon First is founded already more than 19 years ago as then Technobiz, a name which still resonates well. But January 1st, 2021, we carved out and we set the company on a course to build more systems and further integrate photonic integrated circuits on interrogators based on fiber break ratings. We are currently a team of 40 people located in Alkmaar, the Netherlands, in a Dutch spectrum of integrated photonics. We have a 500 square meter clean room in Alkmaar where we have our own packaging, research, development. We build our own interrogators. We work with our own sensors, and we embed also those sensors inside an on-site composite structure. We're a blend of quite a young team with people who've been with the company for already 14, 15 years from the Technobiz era. But also a lot of new people coming in, building the company around that great heritage which Pim Kat, the founder of Technobiz, left in my hands. What do we do? Photon First basically is a supplier of smart data. We turn light into valuable data and allow our customers to make smarter decision making at scale. As most of you know, and I see a lot of familiar names in the list, so nice to see everybody who we already work with. We do FPG interrogators and fiber sensing as point sensing, like Remco just really explained well. I do want to add to Remco's saying that not only is point sensing needed for point sensing applications, it's also a very cost-effective way of applying fiber sensing compared to distributed sensing. And I hope put some numbers in that perspective. PIM's dream has always been focused on integration of optics on PICs from a cost curve perspective. And like other FPG interrogator builders, also Technobis Photon First started with a 50K FPG interrogator. The last couple of years, we've been around the 5K, so 5,000 euros, and with the current dollar-euro rating, you can easily also read dollar there. 5K per system. And always with the promise to add more components onto PICs. Not just the spectrometer, but also light sources, a combination of polarization and polarization units, and also optical switching. And I'm happy to report that this year we're launching Gen 3 systems, which are sub 1,000 euro and will read out up to 1,000 FPGs on one fiber for 1,000 euro per interrogator, which is not there in the world, and truly leveraging the fact that PIC-based is the way to go in terms of scalability and in terms of cost effectiveness. How does that work under the hood? This is basically what we call the generations of systems using, and as we go integrating optical components on chips, gluing the chips together. That's why we also do our own packaging at Photon First, and even combining in a next generation of system that with an ASIC to even go below the 100 euros of system. This has always been a price point discussion. However, we also see a huge additional benefit of going PIC-based. The fact that we use PIC-based systems is not only potentially really scalable, and as you can see, really cheap, but it's also basically a solid state system, allowing us to use these interrogators in very harsh environments. We developed multiple customer-specific systems who have DO 180 shock and vibration proof monitoring solutions, aerospace graded interrogator systems, which can rotate 900 RPM while you don't see it back in the signal. This is a miniaturized interrogator with edge computing in the interrogator itself, wirelessly transmitting the real-time data as it rotates 900 writes per minute on top of an Apache helicopter. That's what chip-based sensing can do. Here's a video of the wind tunnel testing of that system itself. And we even launched one into space, surviving minus 53 degrees centigrade and still functioning. So as I said, we've been leveraging this knowledge already for years in developing customer-specific interrogators and doing projects with those. We do that in our own clean room in Alkmaar. We have our own packaging facilities to do so, and we chose to industrialize this packaging of PICs to do that ourselves. Most packaging capabilities in the world are based on datacom, meaning they glue chips and fibers together, which is fine if you want to do Netflix. But if you want to rotate it on top of a helicopter, you need a more sturdy way of coupling, which we developed ourselves. We weld the fiber next to the chip to make it the most sturdy combination possible. This is such a popular packaging capability that we even sell this as an opportunity for others, for example, LiDAR parties and quantum computing parties, which we package their chips in-house in Alkmaar. I'm also happy to say that not only do we help in the back end customers with customer-specific systems, but also if you look now at our website, we're launching a whole variety of systems leveraging the Gen 3 and the harsh environment edge of PICs. We've traditionally had the FPG systems reading out 8 or 64 FPGs on the system. We added edge computing to that, and we add Gen 3 systems, which we call the Nexus family, where the Nexus 100 reads out, surprise, 100 FPGs on one fiber, and Nexus 250, 250 on one fiber, pushing that to 1,000. And to come back to Bram's question to Remco, we truly believe you can push the amount of FPGs on one fiber, which we are doing, but at the cost effectiveness of these solutions, with edge computing at the interrogator itself, a decentralized approach of these interrogators and multiple communicating with each other creates a more cost-effective web of the total solution. And again, that's the only thing what PIC can do. I do have to come to the conclusion that selling just interrogators is a difficult task. A lot of potential customers need to see it happening in the field. That's why we also invested heavily with DLR and NLR, the Dutch and German aerospace laboratories, in applying our fiber knowledge on rotating assets, meaning windmills, but also obviously in defense applications. Here you see a couple of examples where we embed fibers inside composite structures or on composite structures to do basically a whole shape deflection or impact detection of composite blades, what you see in the middle. And if needed, we can even do a complete shape sensing of a fiber with our interrogators as well. To finalize, Photon First delivers and has been delivering for years in the traditional fiber sensing applications like structural health monitoring, bridges, transformers, on the railway side, in aerospace. But what you typically see now in the last couple of years, that harsh environments really leverage PICs, not only for the cost effectiveness, but also in literally space launching systems. I'm happy that Europe is catching up to the US in reusable space rockets, and happy to report that we're in both, and even on rotating assets in the field. So that's where we are today, and I hope I inspired you a bit to see where we're heading in the next couple of years to further integrate solutions on PICs. If anybody likes to talk further, or we can help you with collaborating with each and one of you, or support you with fiber sensing systems, then please reach out. Always happy to have a chat, and that might lead to another nice partnership.
Thank you so much, Linda, on the incredible work you are achieving with PICs. I'd like to bring in a couple of companies who also make this kind of work possible themselves. So thanks to NVIDIA, silicon photonics is very topical this week. So I'd like to bring in Dr. Jake Bielli, CEO of OPTICA corporate member Light Trace Photonics, to introduce their pipeline for accelerated integrated photonic development to help unlock new applications like this that Photon First have been doing. Jake, the floor is yours.
Thanks, John. I'm just sharing my screen.
Yes.
There we go. Hopefully you can see that.
Yep, it's come through.
Great. Okay, yeah, thank you. Thank you for the invite to speak here. We've heard some really interesting talks about what fiber sensing can do. And yeah, really great to see Photon First as well, the technology you guys have put together. Really awesome stuff. Light Trace Photonics is not a company developing optical fiber sensing. It is a company that helps companies like yourselves to actually take on and develop integrated photonics into their products. And what we do at Light Trace is we help companies do that quickly and effectively. So it probably won't come as a surprise to many of you that actually to sit down and start thinking about developing an integrated photonic product is quite a daunting challenge. There's a very fast-moving ecosystem. You know, even over the last few months, we've had new technology platforms being announced. You couple that with a shortage of engineers and a lack of kind of trusted IP available, then it becomes very difficult to sit down and actually plan how do we develop an integrated photonic product without, you know, spiraling costs and hidden risks. So at Light Trace Photonics, our approach is simple. We use our expertise to minimize the risk and maximize the results to support companies going from idea all the way through to product launch. And the way we do that is kind of across these four key steps. So we will engage companies to help them understand, firstly, you know, is PIC technology right for them? Is it feasible? We can help do some training with the engineers as well and have them actually get hands-on with integrated photonics. Once we've got a solid plan, then we help companies to actually put down a first-time right design on a chip. And we do this by providing access to proven component IP that we've developed in combination with our understanding of the ecosystem and the fabrication process, and we will actually help get a design down that is likely to work first time, which is really key when you're trying to demonstrate the value of a technology and you don't have much money available to do that. Once the chip actually comes back, we can help out on the test and measurement side. So we are not just a design house. We handle hardware. So we understand how to test and measure these components. It's really important for making sound decisions moving further through the product development cycle. And then finally, we have the LightPort Pro, which is effectively a circuit on a chip evaluation board, which enables engineers who are not used to engaging with integrated photonics to actually program and utilize integrated photonic circuits without having to learn how to couple into them and all the other barriers that come with actually trying to interrogate a photonic circuit when it hasn't been packaged. So that's our approach. What kind of sets us apart from other companies that help with this kind of development is that we've actually done it before. So we've actually taken a product from idea all the way through to the market. It's the LightPort Edgy, as you can see pictured on the right here. And it's got a complex silicon nitride photonic integrated circuit in there. And the process of actually taking a product from idea all the way through to the market, it's given us a real understanding of the hidden challenges and the hidden risks there. So yeah, that's kind of what the unique offering that we can bring to the party is, that we've actually trodden that road before. So we've got 15 years of combined experience actually developing integrated circuits. Our team were trained in actually integrated photonics for quantum applications, which has really given us a solid understanding of how to develop advanced integrated photonic components. So you can go to many foundries and you can see their list of components available, but typically they won't have been designed and optimized for your specific application. And what we can do is apply our knowledge to actually develop IP and a system that really is optimal for your application. We've got a really strong network in the ecosystem, and we have the ability to work and point you towards the best foundry for your actual application, and similarly to the packaging providers as well, to help turn that product into a reality. So yeah, that's Light Trace Photonics. What we can do for you is we can help you get your fiber-based sensing products to market quicker, utilizing integrated photonics. And in terms of what you can do for us, you can help us understand as a company, what are the technical barriers, what are the commercial barriers for uptake of integrated photonics in fiber sensing, and what are the key kind of values you see of employing integrated photonics for fiber sensing in terms of new potential markets or new applications. We're keen to understand what we can help enable in your industry. Yeah, thanks for listening, and I'm happy to take any questions you might have.
Great, thank you so much, Jake. And of course, to produce these next generation systems based on PICs, like you've shown in your slide there, we need reliable commercial PIC foundries that are capable of volume production. So I'd like to welcome next Dr. Steen Kuivers, Technical Project and Sales Manager for Switzerland-based, great supporter of OPTICA Ligentech. Steen, tell us how you can help the fiber sensing industry.
Thank you, John, for the introduction, and good afternoon, everyone. So I'm Stan, and most of you are already familiar probably with Ligentech. So Ligentech is a manufacturing partner for silicon nitride-based photonic integrated circuits. So besides the typical foundry services of actually manufacturing these PICs, we also support with design, layout, and testing of these circuits. And specifically for the fiber sensing community, what we do, and that's already highlighted in the previous two presentations, well, these PICs are typically used for the fiber sensing interrogators, as they make the overall fiber sensing system more affordable, robust, and compact to be deployed at scale in difficult environments. And I would like to maybe highlight three. Sorry, can you see my second slide, by the way, or is it still?
Sorry, your slides aren't showing. So I should
Oh,
have mentioned
sorry.
that.
Oh,
Please
sorry.
share.
1 second. Okay, now I
There we
guess you can see my slide.
Yep, we can see. Thanks.
Okay, sorry for that. So coming back to where PICs are used for fiber sensing systems, they're typically used for the fiber sensing interrogators. And I would like to highlight maybe 3 features of where silicon nitride-based photonic circuits can stand out for fiber sensing systems. Well, a first feature is that we can implement the passive functionalities with low insertion and propagation losses to ensure uncompromised signal quality. And that can be, for example, for demultiplexing the signals or for building optical filters used in the fiber sensing interrogator. The second feature is that we at LIGENTEC also integrate the active components on the silicon nitride chip. Those can be, for example, modulators or also photodetectors, so that you basically have all the essential functionalities or all the essential building blocks on a single circuit. And also importantly is that all these silicon nitride PICs, they are manufactured in our automotive qualified 200mm fab to make sure that we meet the quality standards that are required for this industry, but also that we provide the direct scaling path to our customers in this field. To give maybe a very brief example of where these how such a PIC would look like, we've built roughly a year and a half ago a small demonstrator chip where we integrated a photodiode array using microtransfer printing. So basically what we do here is we have a pre-processed indium phosphide wafer with a lot of photodiodes on top of it, on top of the wafer, and then we pick and place many of those photodiodes in parallel to print them on the silicon nitride circuit. So here you can see a small microscope picture of such a photodiode. And then in addition, on the same chip, we also integrate the arrayed waveguide grating to build the full spectrometer circuit. And here we can benefit immediately from the low insertion and propagation losses of the silicon nitride, as well as the low phase errors and low temperature dependence of silicon nitride, allowing us to have a stable platform for AWG development. So this could, for example, be used in a fiber sensing interrogator. So that was a very quick overview. If you want to learn more about our PIC manufacturing services and what we can do for you, we are very welcome to reach out to us, and we can discuss in more detail.
Thank you so much, Steen. So we're now going to change gear a bit from PICs. We're going to welcome an industry collaboration showing how multi-core fiber fanouts from OPTICA corporate member Chiral Photonics are integrated at the system level by FPGS for fiber shape sensing applications. So Dr. Bram van Ho, Director of Sales and Marketing at FPGS, and starting with Dan Negroschel, President and CEO at Chiral Photonics. The floor and the attention of everyone is yours.
Thank you, John. I hope everybody can see my slides.
Yep.
Chiral Photonics is a 25-year-old company that's been making fiber-based components. And we're going to lead into FPGS, who is making shape sensing systems, among other things. Just to tell you a little bit, and for those of you who aren't familiar with the multi-core fibers, this is a cross-section of a single core fiber that most people are familiar with. These are examples of multi-core fibers. We've worked with fibers anywhere from 2 channels to 22 channels, I think is the most that we've worked with now. And these fibers were primarily developed for communications for the last 2 decades or so, especially for submarine systems that are starting to use them. The first submarine cables are going under the sea now. But sensing has been an ongoing interest from the beginning. Today we'll speak a little bit about 3D shape sensing. And those 3D shape sensing systems actually beat communications to the market. There were commercial systems being used in biomedical fields starting in 2019. Just to give you an idea of what we do, we make these fan-outs. These are small devices that allow you to access all the individual cores. So most of the fiber manufacturers can't even fully test these multi-core fibers and then until they can get light into all of the channels of these fibers. So these are small devices called fanouts, and you can see here examples of 4-core fanouts, 2-core fanouts, and 19-core fanouts. They give access to the individual cores of the fiber, and they also allow these fibers to be seamlessly integrated into the ubiquitous single core fiber network. So now you can use these fibers and you can use all the tools that you would normally use for interrogating or communicating via these fibers. For different applications, these components have been qualified for telecordia, submarine, biomedical applications, and a number of different applications. So why do you want to use these multi-core fibers? For communications, the answer is bandwidth density. You have to fit more information into the same, most of these fibers are the same OD, the same outer diameter as standard fibers, 125 micron fibers, so they can be used with standard equipment that's available today. So if you need higher bandwidth density, that's one reason. For sensing applications, there are a myriad of reasons. We'll speak a little bit, FBGS will cover 3D shape sensing. For different interferometric sensing applications, you often want equal path lengths for all of the channels. You can't get more equal than running them all within the same single fiber. And also, for those types of applications, you often want those channels to be feeling the same environment as all the other channels. So that also is accomplished by putting them in a single fiber. There are many flavors of multi-core fibers also. They're not always homogeneous as shown here where all the channels are the same. Sometimes you'll have a heterogeneous fiber where some channels, for instance, might be used for collection, some for emission. You can run power over fiber to places that you can't get power to easily. And this multi-core fiber ecosystem is mature now. So there's a growing number of multi-core fibers that are commercially available, and there are many, many more that are custom multi-core fibers. They use standard splicing, automated splicing tools like are shown here. These are, and there are additional ones. Many of them are automated, some of them are not. Some of them are meant to be used manually. So like I mentioned, the first submarine cable is in production. So fanouts are in production, both for telecom and for sensing applications. And additional multi-core fibers that we've been involved with include WDMs for putting in different wavelengths, attenuators, connectors. And there's a growing base of users and trained technicians who are trained on working with multi-core fibers. But again, through the use of some of these components, you can use them in the standard single core network. And let me hand off now to FBGS to speak more about the 3D shape sensing application. Thank you.
Thank you very much. Then I will take over the screen, if I may. I hope you can see my screen. So good day to all of you. Thank you, John, Jose, and OPTICA for giving me the opportunity to present one of our key applications related to shape sensing. And thank you, Dan, for the good introduction and the explanation on multi-core fibers, fan-outs, and all the related technology. I know we are also running short on time, I think, so we'll try to keep it concise and quickly come to the application. I just have one slide introducing the company FBGS. So we're developing, manufacturing fiber optic sensor components and fiber optic sensor solutions based on fiber Bragg ratings. We tackle a broad variety in sensing applications, ranging from temperature sensing, strain sensing, pressure sensing, but also then covering shape and force. That is the topic of this presentation. And the focus for shape and force sensing is on medical applications. So quite different from many of the presentations we've seen earlier. We switch a bit gears to the medical field. We are manufacturing in Europe. We have offices in Germany and in Belgium, but we're worldwide active with sales offices and partners in US, but also China, South America, and so on. The base technologies we make use of, first of all, we have our draw tower grading technology, referring to the combination of fiber drawing and grading inscription. That's also the technology or the manufacturing process we use to produce our multi-core fibers and to inscribe gradings in these fibers during the drawing process. Comes with economies of scale. So for mass producing optical fibers with Bragg ratings, this is by far the most economical way of doing this because it's a fully automated process. We can draw kilometers of fiber in a single day with minimal manual intervention. We can also write through the coating of an optical fiber using ultra-short laser pulses, using femtosecond laser pulses, resulting in femtosecond gradings. And then the third technology or the third part of our product portfolio is related to the interrogation platforms, where we have our FBG scan platform covering a wide range of applications from quite simple WDM sensor platforms all the way to the infinity scan, so allowing to interrogate thousands of measurement points, thousands of FBGs along a single optical line. Coming then to the solution offering in medical or for medical applications. You see here on the left a number of application areas or companies or application fields where we were active in. If you Google these application fields, you will easily find a lot of big companies where we're working with. We have indeed the first systems also being commercialized as we speak. We actually combine the draw tower grading technology using multi-core fibers together with fan-outs, sensor assemblies. So we start from multi-core fiber, apply a multi-core connector, put the fiber into a housing, perform calibration procedures, and so on. And we, of course, make sure that the overall system, the combination with the interrogator, our so-called shape scan, is fully enabling a turnkey shape sensing solution. You see some screenshots, some pictures of how an overall system then looks like. The software is basically allowing for 3D shape visualization in real time. Is also allowing to stream the data further on in customer platforms. And a lot of customization is there done specifically for projects driven by customers. Such a starter kit or such a base shape sensing kit then consists of a so-called shape probe. You see here on the left, fiber typically put into a metal tube to protect the fiber from compressive forces, to avoid non-uniform strain effects, to also reduce twist effects. That sensor assembly is built in-house at FBGS. We do full calibration of that as well. Connectorization is also happening on our side. And then there is the platform, the shape scan platform, as shown here on the right, with an integrated fan-out, taking in a multi-core fiber sensor and converting the optical signal immediately into real-time shape information. A next development or new development we're working on is basically using augmented reality, where we allow the user to basically pinpoint the origin of the shape anywhere in space, and actually combining then the shape information coming from the multi-core fiber with other technologies, and basically creating the possibility to have anchoring or the possibility to anchor objects in the user's world or in the doctor's world, and combining that with other real-time informations. To show you how the platform or how the system works, I mean, here we have a multi-core fiber or a shape sensor embedded into a catheter device, where actually the top 15-20 centimeters is instrumented with Bragg ratings and multi-core fiber. You see on the screen in the back that the shape is represented in the software. And actually, this movie is showing a different visualization, but comes down to the same sensing platform, showing 3D shape using a flexible nitinol-based shape sensor. And what is then also next in the movie is another application or another measurement that can be picked up using the same technology, more specifically tip force. So making use of the same multicore fiber and then adding a transducing element to the fiber, it's possible to do at the same time shape sensing along the length of the fiber and also measuring the directional force at the tip of the sensor, as you can see here in the movie. We isolate the fiber or we isolate the sensor from actual strain effects. So it's important to mention here that this is a directional force sensor that is not prone to strain or temperature effects. I rushed a bit through, but I would like to thank you for your attention. And of course, if there are questions, I'm happy to answer them. And we can also, of course, talk offline on your shape sensing application and your fiber sensing needs.
Not as much, Bram and Dan, as I would like to thank you. Congratulations, first of all, of finding reasons for working together. And second, I know for many years, Carol Photonics has been making fantastic fan out for multicore fiber. Being able to use them for this application that Bram has been working on for many years is fantastic. One quick question for you, Bram. During this meeting, we have been discussing a lot about companies wanting to do the fiber or wanting to do the interrogator. You actually are doing both for a particular application for fiber sensing, for shape sensing. Why did you decide to do that?
Very good question. We decided to do that because we actually experienced that it is key to ensure that the fiber and the interrogator are one-to-one matched, or that the compatibility between all the building blocks involved in the system is there. And especially when combining gratings in multicore fibers, there are a lot of restrictions and technical aspects that need to be safeguarded on the interrogation platform as well. So building a full system all the way from the interrogator up to the fiber is actually key there to ensure that the overall performance of the system is maximized and that all the building blocks are actually also communicating and interacting well with each other.
Dan, connectorizing multicore fiber is challenging, it's difficult. The standard connectors are expensive. How do you evaluate two-photon polymerization to do this connectivity?
I'm not sure if I understood the last part of that question. So
we are going to introduce you to two companies very active in two-photon polymerization. And then I will come back to you and say, can you use them to connectorize multicore fiber? The first one, we're going to go to Keystone Photonics. Roman Sahelski, please let us know what you do at Keystone Photonics and how can you help companies like Dan's Chiral Photonics all the way in New Jersey?
Yes, thank you very much for this flattering introduction. I understand we run out of time, so I will just try to keep it short and give you a 1-2 minute pitch. So I would like to start with a definition of classic fiber sensor. So typically we have fiber break rating, and if we, for example, heat fiber, heat up the fiber, for example, and then if we measure reflected or transmitted wavelengths, transmitted light, then we can actually measure the temperature change or strain change and other characteristics. But what we do at Keystone Photonics is something different. So first of all, we don't heat fibers, but what we do is we fabricate fibers, or we fabricate microstructures directly on fibers. So we use technology, as you said, 3D laser printing or 3D two-photon polymerization, and we have capabilities to in situ fabricate micro-optical structure directly on a fiber core. So this is how it looks schematically, and this is how it looks in real life. So this is a cross-section of a fiber array with printed structures by Keystone Photonics. So our typical product is, well, not this globe, so this globe represents freeform structure, but our typical product is here on the right. So this is mirrored lens that can focus light into any direction, in this case in 90 degrees. And this really actually focuses into Karlsruhe, Germany, so the place we're located where Keystone Photonics is based. So our typical market is wafer level testing or optical wafer level testing. So we're mainly dominating market right now. So the main manufacturer of optical fiber probes. We collaborate with all major players in this area in the optical wafer level testing. So we produce innovative solutions for optical coupling. So we produce both for trench coupling, as you can see on this slide, and also for grating coupling. But we also trying to explore other possibilities on how we can expand area of applications. So we're a really fast growing startup company, and one of the applications, which is one of the development of Keystone Photonics, is optical distance sensor or optical distance sensor. So basically what we do is we produce lens here, which can introduce a point of best coupling. So basically if you move your fiber in Z back and forth, and you collect back scattered signal, you can actually achieve the point of best coupling, and basically then you can calibrate your fiber and distance between your fiber and your surface, for example, of the trench or of your waveform, very precisely. So you do not need any capacitive or any other distance sensing devices. So this is one of the possible solutions to fiber sensing, but we are really open to your applications. So if you have anything in mind, please reach out to us. You can write me, you can write on Keystone Photonics sales email, and we really want to explore and expand our possibilities because we believe we can use our technology. For example, in spectroscopy, we're also trying to expand in space applications. And if you have anything in mind, please reach out. Thank you.
Thank you very much. And going from, of course, Keystone to Nanoscribe, Jörg Smolensky. Also tell us how the Quantum X can help companies like Chiral Photonics on characterizing specialty fibers. Jörg, we cannot hear you. 1, 2, 3, Jörg.
Can you hear me now?
Now I can hear you. Oof, now I can.
Yeah, there were two buttons, one on the headphone and one on the screen. That's too much. Okay, I just want to introduce you to what we can do as a manufacturer of equipment for 2-photon polymerization, so micro 3D printing, to print optics on for fiber sensing. So we have a platform, Quantum X Align, which enables this automatically. So we have a software, basically easy setup. You can see different optical elements on fibers. These are fiber arrays. We can print on multi-core fibers, as shown by Chiral Photonics. We can print on endoscopes. We have standard elements for printing different widths of V grooves, fiber bundles. We have printed on fiber bundles with up to 10,000 cores for imaging applications. We have here on the right side, you can see the hardware we have. Basically, it's a look in our system. We have a patented way to print on fibers, aligned precisely, different element of optical elements. And with our system, we can think that this can be done for single fibers, for batch processing of fibers. Even on PIC, we can print this. So this Steen and Leander mentioned this from Photon First, that they use PIC for optical sensing. And we can enable better coupling, passive alignment with printed optics on these elements. So we do the manufacturing side of we do the equipment, basically. We do feasibility studies for you, so where we can help to validate the technology. And then we have companies out in the market like Fix or Print Optics who can do drop shop, or if it fits, you can have a system at your site. We're happy to discuss about this. Such some inspirational things. We can also print mechano-optical things, I think, here like a fiber clamp. And the shapes we can print are endlessly, like this periscopes, tapers, collimating lenses, anything you want. So I hope it was fast enough. If you want to meet me, I'm at OFC next week, booth 5110, and we can discuss live one-to-one about anything you need.
I also will be at OFC next week, and I think many of us look forward to seeing you all. As usual in these meetings, we keep the best, the most innovative, something new for the last. And I am more than happy to welcome for the first time, and for the first of many times at an Optica event, Michael Forge from Q-Libri. Tell us about a different type of fiber facet sensing. The floor is yours.
Thank you for the nice introduction, and thanks for having me here. Today, I'm Michael Förk, co-founder of Q-Libri, And we are a startup actually coming from the area of quantum optics and therefore are new to this whole sensing community. And therefore, give me one slide for introducing who we are. So a couple of years ago, we started as a spin-off here in Munich from LMU and MPQ, collected some public money in order to build our first products. And those products are quantum sensing hardware. And we incorporated then in 2022 and started selling those and making us a profitable startup. Since then, we have grown. So currently we are 23 people and we have global sales structures and we want to expand to new directions. One of them is microscopy and the other one is actually filters and sensing. And that's what I would like to talk about today. So what is the technology we are using? The technology, as you might know, is based on optical fibers, but which can be of different kinds. And here you can see an end facet of such a fiber. And what we now do, we shoot with a laser on this fiber in order to ablate a small concave structure. This is on the size of a couple of micrometers and can also be custom designed. And if you now add a highly reflective coating on this end facet, which also can be designed to your needs, you get a tiny curved mirror. And this tiny curved mirror, if it now faces a similar one, builds up a stable optical resonator where the light can bounce forth and back between those two mirrors up to 100,000 of times. Now, what can you do with this? First of all, you can think about a nice packaging, but the very straightforward and easy solution is, you can now use this as a tunable filter. And with tunable, I mean, you can now tune these two fibers from basically touching to tens or hundreds of microns, giving you the possibility of tuning your free spectral range, tuning your line width, and so on. Of course, where we come from is a different field. It's the field of quantum optics. Here, an example of customers of us from Harvard, they used such a system and put in single atoms between those two fibers in order to build high-fidelity quantum gates for quantum computing. Of course, you cannot only use single atoms, but you can also use, for example, gases or liquids like done here, where people put in single molecules or single DNA strands in a microfluidic channel in order to highly sensitive detect and profile them. And of course, all these applications can only work if the distance between those two mirrors is controlled down to a subatomic scale. And this, you can now also do the other way around. You can basically use this distance control in order to sense any changes of the distance or vibrations from the length scales of picometers up to micrometers. Now, I tried to sketch a bit what we can do for you, answering the Optica question. Now, what you can do for us, we are always happy to talk about any sort of mounting solutions for these fibers, about packaging, and about your ideas where you think this could be nicely applicable to the area of fiber sensing. And with this, I would like to thank you for your attention.
And I would like to thank you for the great contribution. I would like to apologize to everyone that we ran out a bit of time. This topic today required a bit of time because there are many companies who have worked really hard for many years on fiber sensing, and we couldn't leave anyone out. We cannot do this. And we could have spoken for many hours because we have companies like Lithium, like Melcano, like Fast Laser that also wanted to speak. We also even had Alcatel Submarine Networks in the room. It was impossible. We did our best, but allow me to close the meeting right now and thank the people in YouTube. For those of you who want to stay after the closing credits, we'll be here for a couple of minutes to keep a beer discussion as usual. All right, allow me to ask IT to disconnect the YouTube stream. So IT has disconnected, and now we can breathe. Great job. Congratulations. I really enjoyed the meeting so far. Michael Forge, interesting. You are going in the right direction. How many people are you now at Culibri?